the last lecture, we had discussed about inferencing mechanism in first order predicate logic. We ended with the example of inferencing, where we had eliminated universal quantifiers, we had eliminated existential quantifiers, and then we had also at times we had introduced existential quantifiers. We have also seen how two very important operators are used. One is substitution, another is unification. Now, one very powerful inferencing mechanism that is used in inferencing in first order predicate logic is resolution. Resolution is an inferencing method that is sound, and it can be automated as well. So, today before we today we will be discussing in this lecture how we make inferences using the resolution method. Now, before we start discussing about resolution technique as applied in first order predicate logic, we will have a brief revisit, a revision of how it was applied in propositional logic. We had discussed that earlier also. So, let us quickly have a recapitulation of how resolution was applied in propositional logic, and then we will see how it can be applied in the case of predicate logic. So, here the basic principle is that suppose x is a literal and S1 and S2 are two sets of propositional sentences. Right now, we are not discussing predicate logic cases, we are restricting ourselves to propositional logic cases. And what is the basic difference between propositional logic and predicate logic, as we have seen? First, in predicate logic we can have variables, whereas in propositional logic the parameters are all constant. And the second difference is that in predicate logic we can have quantifiers over these variables, and mainly there are two types of quantifiers, existential quantifier and universal quantifier, and such quantification is not there in propositional logic. So, here suppose S1 and S2 are two sets of propositional sentences represented in the clausal form. We already know what is a clausal form. Clause is a disjunction of literals. And also we mentioned what is a horn clause. Horn clause, just in the last lecture we had discussed that on the right hand side of the implication there can be only one literal. That means, in the clausal form there can be at most one non-negative literal, because say P and Q implies R. In that case, if I make it in the clausal form, P and Q implies R. If I convert it into the clausal form, it will become not P or not Q implies or not P or not Q or R, right. So, if there be only one non-negative literal, if there can be only one literal on the right hand side and the left hand side are all conjunctions, then we will have it when converted in the clausal form at most one non-negative literal. So, but clause is a disjunction of literals. So, suppose x is a literal and S1 and S2 are two sets of propositional sentences which we have represented in the clausal form. If we have x or S1 and not x or S2, then we get S1 or S2. You see, if look at this, this is a revisit. We have already shown the same slides while discussing the propositional calculus. So, here if I just do this and, then obviously x and not x, that part will vanish, sorry, x or not x, that will be always true. So, S1 or S2 it will come to. Here S1 or S2, this entire thing is called the resolvent. That means, these two we have resolved, these two we have resolved in order to get this, all right, and x has been resolved upon, all right. So, the example, the same old example, if a triangle is equilateral, then it is isosceles. If a triangle is isosceles, then the two sides AB and AC are equal. If AB and AC are equal, then angle B and angle C are equal. ABC is an equilateral triangle, and we are supposed to prove angle B is equal to angle C. Now, given this, now we next represent these in the form of propositions. If a triangle is equilateral, then it is isosceles. So, we can write equilateral ABC implies isosceles ABC. If a triangle is isosceles, then the two sides AB and AC are equal. That we can represent as isosceles ABC implies equal AB AC. If AB and AC are equal, then angle B and angle C are equal. Written in the predicate form, it turns out to be equal AB AC implies equal B and C, where B and C are angles. ABC is an equilateral triangle. So, we simply can write equilateral ABC. Now, what is the next step? We have to convert them to clausal form. Now, we had equilateral ABC implies isosceles ABC. Converted to clause, it becomes not equilateral ABC or isosceles ABC. Isosceles ABC implies equal ABAC, not that one translates to not isosceles ABC or equal ABAC. Similarly, equal ABAC implies equal BC gets converted to not equal ABAC. Why is this not? Because if I convert it in the clausal form, this antecedent part becomes negated. I am sorry, here there is a mistake. Not equal AC, this should be changed to or, right, just as has happened here. Not equal ABAC or equal BC. Okay. Please correct it in your note. This part where the mouse pointer is pointing to should be converted to or. And next one is equilateral ABC. So, now we have got all these in the clausal form. Now, resolution is the basic approach of resolution is proof by refutation. Now, that means to prove that angle B is equal to angle C, that is equal BC, our approach is, let us disprove that B and C are not unequal. This is a very well known proof method, where in order to prove that B and C are equal, we first try to prove B and C are not equal and fail to prove it. So, we try to disprove not equal BC. Okay. So, our goal or objective is to prove this equal BC. So, we start with not equal BC, we start with not equal BC and we try to disprove it. So, what is that? We take the clausal form of the goal and negate it, all right, and try to disprove it. That is our approach. So, let us look at this animated resolution. We have got in our knowledge base all these clauses, equilateral ABC or isosceles ABC, etc., all these that we have discussed, and this is the one we want to prove. We want to disprove this not equal BC, we want to disprove it. So, in order to prove equal BC, we want to disprove not equal BC, and then we have to resolve it, and from here we will have to select one clause where we have got the negation of this equal BC. Where is that? That is here equal BC. It is not equal BC and here is equal BC. So, I select this clause and take this not equal ABAC or equal BC. Now, this part and this part will resolve out together and we get not equal AB and AC, not equal ABAC. Okay. So, this is the first level resolvent. Now, we have to find a clause when the dual of not equal ABAC, this equal ABAC is there. So, that is this one. So, I now try to resolve this resolvent with this clause, and as I do it, what do I get? Equal ABAC and not equal ABAC resolve out and resolved upon, and we will get not isosceles ABC here. So, this is the new resolvent, and not isosceles ABC, we start with that, and which one should we select? Obviously, this one, because this one has got the negation of this. Here isosceles ABC is there. So, I select this, and as I resolve these two, what do I get? These two again resolve out, I get not equilateral ABC. And when I resolve out not equilateral ABC with this one equilateral ABC, what do I get? I get a null clause. That means, the point from where I started is disproved. By resolving, this is a null clause, that means, I am trying to resolve two contradictions. That means, the objective, the goal with which I started is not consistent with the knowledge base that I have. With the given knowledge base, the goal which I started with is contradicting. Now, what was the goal? The goal was the negation of the goal that I actually wanted to prove. So, the negation of the goal that I wanted to prove is disproved. Therefore, the actual goal is proved. That is the principle of resolution, and the same principle will hold for resolution in case of predicate logic as well. Next, let us quickly see what is the basic, what are the basic steps of carrying out resolution for propositional calculus. First step is, we convert the given propositions into clausal form. Next, we convert the negation of the sentence to be proved. Please note that we take the sentence to be proved and we then first negate it, and after this negation we convert it to the clausal form. So, convert the negation of the sentence to be proved into clausal form, combine all the clauses in a set, and then iteratively apply resolution to the set when we take. So, one of the candidates that we start with is the clausal form of the negation of the goal that I want to disprove. So, I take that one and take a suitable clause from the remaining clauses in the set and try to resolve them. As if the resolution is possible, then through this resolution I will get a new clause. Then I take that new clause and take another one and try to resolve it further until all the clauses are exhausted or I come across a contradiction, that is a null clause. As soon as I get a null clause, then I immediately prove that the negation of the goal is contradicted, therefore, the goal is true. So, I iteratively apply resolution to the set and add the resolvent of every iteration to the set. Okay. Then we continue until no further resolvents can be obtained or a null clause is obtained. That is where we stop. That is the way resolution works, and we have seen it through an example. Next, when we try to do it for predicate logic. There will be some differences, but the major principle of resolution is remaining the same. The major approach is remaining the same. Here also we will start with the negation of the goal, convert it into clausal form, and the procedure of generation of resolvents are the same. However, since you realize that we are now going to deal with predicate logic and not with propositional logic, we will have to handle the cases of variables as well as quantifiers. And in the last lecture, we have already seen that how these quantifiers can be handled and how we can get the clausal forms. So, those steps have to be followed in order to apply resolution for first order predicate logic as well. So, let us start with another set of examples. Let us consider a few statements as shown here. Excuse me. All people who are graduating are happy. All happy people smile. Someone is graduating. Is someone smiling? That is the conclusion, okay, that I want to prove. I mean, here it has been posed as, is someone smiling? I want to have an answer yes or no, but that is equivalent to proving a statement, someone is smiling. Someone is smiling. Now, if that is proved, that is, if then the answer is, if someone is smiling, its answer is yes. If it is disproved, someone is smiling. If that is disproved, that means no one is smiling, then is someone smiling? The answer to that is no. Now, if you look at these sentences, you will soon realize that none of these sentences can be really represented in the form of propositional logic. Now, all people who are graduating, let us forget about mechanical inferencing for the time being. If we just apply our common sense reasoning, let us see what comes up. All people who are graduating are happy. All happy people smile. Therefore, I can reason and say all people who are graduating are smiling, and then someone is graduating. That means, there is at least one person who is graduating, and anybody who is graduating is smiling. So, is someone smiling? Should be yes, or if I write that someone is smiling, that would be proved, should be proved, right, from common sense. But however, a computer will not apply common sense in that way. It needs a mechanical procedure by which the same reasoning can be carried out. So, first thing first, we intend to code this problem in first order predicate calculus, and then we will use resolution refutation. This is also known, this resolution is also known as resolution refutation. Now, why is this word refutation coming in? You can very simply guess. What are we trying to refute? In order to prove a particular goal G, we are trying to refute not G, and if we can refute not G, then we are proving G, right. So, that is what is resolution all about. So, we are using resolution refutation to solve a problem. And what is solving a problem? Solving means whether the conclusion can be answered from the given set of sentences. The conclusion that we had expected, or the is someone smiling, that thing, whether that can be proved, okay, using whatever is there. Now, in order to capture the sentences that we had shown just a few minutes back, we will have to first convert them in the form of predicates. So, let us select some predicates. So, in order to make the statement X is graduating, someone is graduating, we have to select a predicate, and we have selected a predicate graduating X, that shows X is graduating. We use happy X. Actually, strictly speaking, depending on the language, actual language, programming language that we will be using, there will be some syntaxes. Here I have taken some unnecessary liberty. Maybe a convention should have been followed that all these predicates should start with a small letter, but forget it for the time being. X is happy, I can write as happy X. X is smiling, smiling X. Okay. Now, we try to encode these sentences into predicate logic using the predicates that I have just now stated. All people who are graduating are happy. Now, that can certainly be written as for all X, graduating X implies happy X. All people who are graduating are happy, and that is universal quantification, no problem with that. All happy people smile, that is again universal quantification, all right. Someone is graduating. Now, what is the, you should have done that, here it has been shown, but you could have also done that. Someone is graduating, that means there exists an X. This parenthesis is not required, frankly speaking, here, because there is no scope of confusion. There exists X such that graduating X, that is someone is graduating. Is someone smiling? Now, that was my objective, but let us consider that this statement is someone is smiling. That means, there exists X such that smiling X is true. Okay. So, if there exists X, smiling X is found to be true, then the answer to this question is someone smiling is yes. So, these are, so the first step was selecting the suitable predicates, and once the suitable predicates are chosen, then the next step that we do is we write down these sentences, express those sentences using predicate logic, using implication, using quantifiers. But the next step would be, we take these predicates here as they are, but here I have made a small change. Is someone smiling or someone is smiling was stated as there exists X such that smiling X. So, that has been converted to, now that was the conclusion, and the negation of the conclusion therefore is there does not exist X such that smiling X. If I can prove this, that there does not exist X such that smiling X, that means no one is smiling. Okay. But if I disprove it, that means someone is smiling. So, we first negate the conclusion and keep the others as they are. I have not made any change in these, but next step we have to convert them into clausal form. In order to convert them to clausal form, the first step would be to eliminate the implication sign, to eliminate the implication operation, right. And to eliminate this implication operation, you know that we will take this clause for example. You see, we are retaining this for all X for the time being, and graduating X implies happy X will be not graduating X or happy X, right. So, similarly, we can do it for the others. Happy x was implying smiling x. So, that gets converted to not happy x or smiling x. Okay. There exists x graduating x, and this did not have any implication at all, that was as it is, and the second one was also not having any implication. This one, the fourth one, was also not having implication. So, now I have got a set of clauses which are all free of the implication sign. Okay. Now, the next step is to convert them to canonical form. Now, it may be that this canonical form, or often it is called normal form, may be new to you, but let us not get too much bogged down with it. It is a form where the quantifiers are there and we have got disjunctions of literals. Ultimately, we are trying to go to the clausal form. Ultimately, we will get to the clauses, okay? And it is basically a conjunctive normal form. So, there will be disjunctions and there can be disjunctions of clauses. So, here you see the next step to do that is to reduce the scope of negation. All right. So, let us have a quick relook at what we had after doing this elimination. Now, you see, for the first two, the scope of the negation is over this predicate graduating x, all right. And for this, the scope of this negation is over this entire thing, even over this quantifier. So, the scope of the negation is fine over here, I do not make any change here. However, just compare the earlier clause number 4 and the present clause number 4. Here, the scope of negation was over this quantifier as well as this predicate. Now, I want to push this negation as much as close to a particular predicate. So, negation of the existential quantifier is a universal quantifier. All right. For example, I say there does not exist a person, there does not exist any x such that not mortal x, where x is a man, say. So, there does not exist, I can convert it to for all x mortal x. My question was, let me work it out here. Say, so let us look at it in this way. I say that there does not exist a person, there does not exist x such that not mortal x. So, the same meaning is communicated if I say for all people, for all x, mortal x. So, I convert that there exists to for all and not mortal to mortal. Okay. So, I push the negation inside. So, that is exactly what is being done over here. This earlier one gets transferred to for all x, not smiling x. All right. So, you see I have reduced the scope of negation here. Okay. The next thing is that we need to do is we have to standardize the variables apart. It is possible that we can put in the variables, the same variable might have been used at different points. For example, here, right, graduating x, happy x, here again not happy x, smiling x, all those things. All right. So, but when I am trying to do this, what I will try to do is for every clause I will change the different variables. Every clause will have, every sentence will have a distinct variable. Now, if you recollect the idea of unification, now in order to, we will see that this automatically gives rise to some problem, that if we have got different types of variables, then we must have some mechanical means of converting those variables in some way in order that we can do the unification. So, here after we do this, the next thing that we need to do is standardize the variables. So, here you can see that graduating x, happy x or smiling x. So, here we have put in, we have taken different, we take the liberty of using different variables. For all x, not graduating x or happy x. So, this one has got x, this has got y. Now, if there were, if there was a clause like say graduating x and happy y, in that case both x and y are reserved for that clause. In the other clauses we will have to use y, z, p, q, all those things, and only later, as we will see, we will try to see whether these variables can be compared or unified. You remember what we discussed about unification? Unification is the process of finding a particular substitution of variables such that two different clauses become identical. Okay. So, that unification we will have to do anyway. So, here you see, here we have selected y, smiling y. Now, here again we have introduced another one, that is z, and for all w, smiling w. So, here you see we have made a change again. All right. The next thing that we need to do, but still it is not a clause. You can very well realize still it is not a clause. So, let us quickly recapitulate whatever we have done till now. What we have done is we are trying to convert it to clausal form. So, the first step that we did is, we have selected some predicates. After selection of the predicates, we encoded the given sentences in the form of first order predicate logic, and then we negated the goal clause. We negated that goal clause, the goal, and put it in the knowledge base. Then we will start converting them into the canonical form or the clausal form. How do we do it? Now, in order to do that, we will first eliminate the implication sign, and that can be achieved by the simple rule that we have come across so many times, P implies Q is not P or Q. After that, and there also we convert the entire knowledge base including the negation of the goal. All right. After that, we deduce the scope of negation. After the, that is, we try to bring the negation to as close to the variables as much as possible, and in that process we may require to change the quantifiers also. For example, not for all x will become there exists x, all right. Not there exists x will become for all x. Okay. After moving these negation, the reducing the scope of the negation, then we standardize the variables. Once these variables are standardized, then we try to push all the quantifiers to the left. Okay. In this example, the quantifiers were not very much within. So, but there can be complicated clauses like say for example, let us try to do an example. Maybe there can be something like this for all x. I am not bothering about too much of meaning here. Say p x implies there can be something else. There exists y such that q y. It is possible that I may like to express something like this. It is possible. So, in such cases, there are two quantifiers, but ultimately my objective will be to push all the quantifiers to the outside as much as possible. So, the next thing that we try to do is we move all the quantifiers to the left, and using which we get, in this case there was not much of a change, we come to these 4 clauses. Okay. Then we have to start working on elimination of the quantifiers. First of all, let us try to eliminate the existential quantifier, and we are already introduced to the process of skolemization. In the last lecture we had discussed that skolemization is the process of finding a constant or a function for the existentially quantified variable that will make this clause to be true. So, for example, here there was in these two, let us go to the earlier one, here there were no existential quantification at all. The only existential quantification in this case that we had was this, right. That was the only existential quantification. So, what do we do here? It was there exists z such that graduating z. We remove that, and in place of that we find out name 1. Name 1 is a skolemization constant. It is a name that somehow we are finding out who is graduating. So, that particular value of x or z in that case is satisfying this statement graduating x. In the last lecture we had also shown that in some cases we replace it not with a constant, but with a skolemization function. Like in that prime divisibility case, we had selected a function p d, if you recall. Now, so we have removed the existential quantifier, that was a step 5. What is the step? What is the 6th step? We drop all the universal quantifiers, because of the simple reason I do not really need it. By now, I have removed the existential quantifiers. By now, I have reduced the scope of negation to as close as possible to the predicates, and by now I have pushed all the quantifiers to the left, and the existential quantifiers have been removed already. So, what is left is just the universal quantifier, and all these clauses are therefore now implicitly universally quantified. So, I need not specify them any further, and so I can simply drop them. And as I drop them, I get these clauses. Now, in this case again we did not have we have only have of disjuncts. Now, in a canonical form it can be conjuncts of disjuncts. What is a disjunct? Again let us go here. Say I have got P x or Q x, this is a disjunction, and say M x and N x, this is a conjunct, this is a disjunct and this is a conjunct. Now, a canonical form is a conjunction of disjuncts, all right. So, I can say that P x or Q x, if I have a form, and M x or N x. Now, this is or say P Q are already there, say R x, R y, or say G z. Now, this is another disjunct. So, this is a disjunct, this is a disjunct, and I have got a disjunct and disjunct, and I have got a conjunction of this disjunct. So, it is a conjunct, right. So, a canonical form will be a conjunction of disjuncts only, all right, disjuncts only, that is a canonical form. Now, what is the implication of this? The implication of this is, if I have conjunction of disjuncts, say this one in whatever we have written, I just take that as an example, and if you just think a little while, you will realize that once I have conjuncts of disjuncts, then each of these disjuncts I can write down separately. Say this one I can write down, this one I can write down as separately P x or Q x, and this one I can write down separately as R y or G z. Now, according to our definition, both these are clauses, and a conjunction of disjuncts, therefore, each of these disjuncts can be written down as a separate clause, and that is our objective, to convert it in the clausal form. Okay. So, after we have dropped all these quantifiers, we convert to conjunct of disjunct form and make each of these as a separate clause, and we standardize variables apart again. So, that each of these clauses will now have separate variables. These steps do not change the set of clauses in the present problem. So, now we come to the resolution proper, but before that let us come here, that here it is not a very those steps 7 and 8 are not so much important here, because by step 6 here we have already got them in the clausal form. Therefore, we now can apply resolution, and let us recall how should we start resolution. We will start with the clause that is the negation of the goal to be proved, and then from the remaining clauses in our knowledge base, we will select the clause that can resolve with this. So, quickly let us, I would rather suggest that you take a piece of pen and paper and start working that on. So, you will start with this not smiling W, and I will try to resolve with this. With which one should I resolve? I will select from these clauses the clause which has got the complementary or the negation of this. So, obviously, this clause 2 should be selected. I assume you are just working it out on a piece of paper, and if we resolve these two, what do we get? The resolvent is not happy Y, but there is a big question here. We had standardized the variables. You see, in case of propositional logic, the problem was not there, but here, since I have got variables and I have standardized the variables, not smiling W and smiling Y, can they be resolved? They can be resolved only if there is a possibility of a substitution, if there is a possible correct substitution. If I can substitute Y by W, then only I can unify these two, right. Then only this smiling Y and smiling W they will become equivalent, all right. So, merely resolution will not do, and what will be the result of the resolvent? Will it be happy Y? Just let us see. I still suggest that you do not just start copying this part out. You first concentrate on this part only, the first level. So, I have not smiling W, and here I had the clause 2, not happy Y or smiling Y, and I can resolve this only under a substitution where Y substitutes W. I am sorry, W is substituting Y. So, this one becomes happy W, smiling W, and the smiling W and not smiling W resolve out, and I get not happy W, all right. Again, here when I get not happy W, next thing I have to select some clause from here. For example, here it is happy X. So, I will try to unify them. Now, this unification is very important. So, here I selected this graduating X or happy X. So, now I replace this X with W, all right. So, I get happy W, graduating W, I combine these two and I get not graduating W, all right. So, here you see I had replaced for the sake of unification, resolving for the sake of resolution, I substituted Y with W, here I substituted X with W, and there was no contradiction, and I came to not graduating W, and there was a clause graduating name 1. So, now this variable here, this W is substituted with the constant name 1, and with this I resolve. What do I get? A null clause. And what does this null clause imply? It implies that the goal with which we started is contradicted. And what is the goal with which I started? It was negation of the goal to be proven. So, the contradiction of the goal to be proven has been disproved. So, the goal is proved. So, is someone smiling? Yes, someone is smiling. So, you just quickly see what is the major difference between these two: propositional resolution in propositional logic and resolution in predicate logic. The problem is that here we have got variables. So, we had to take some extra pain in order to convert them into clausal form. We had to convert them into clausal form in propositional case also, but here we had to take a little extra pain, and after that we have resolved them, and in order to resolve them we had to unify, we had to do a proper substitution. And so, this is a very powerful inference mechanism that is applied in many mechanical proving, theorem proving systems and other applications. Next, before concluding this lecture, okay, in between let me give you a quiz and you quickly copy that out. Solve the problem. This is the problem that we had solved in the last lecture using, this is the problem we solved in the last lecture using other inference mechanism, but the same problem you try to solve using resolution. Okay. So, this is the same problem. If a perfect square is divisible by a prime p, then it is also divisible by the square of p. Every perfect square is divisible by some prime. 36 is a perfect square. Does there exist a prime q such that the square of q divides 36? So, the same thing you convert it into Clausius form, which we did in the last lecture, and try to apply resolution. Next, we will quickly look at some very interesting application of this resolution theorem proving, answer extraction. Let us have a look at. So, given a set of clauses, a knowledge base, we want to find the answer of to a question. If you are noticing here also, ultimately when we got the null clause, we could answer the question, is someone smiling? We got a null clause because we found that someone, if I had really asked who is smiling, you said that you have proved that someone is smiling. Well, who is smiling? The answer lies here, because here this name 1, which was a constant, at least he or she is smiling. So, that answer is there, but now I want to mechanically have that answer at the leaf of my resolution tree, refutation tree. So, here is a nice problem. We know that all packages, suppose a robot is trying, this example has been taken from the book of N. J. Nielsen. All packages in room 27, a particular room, are smaller than those in room 28. Room 28 can have some smaller packages also, but all packages in room 27 are smaller than those in room 28. Package A is either in room 27 or in room 28, the robot does not know. Package B is in room 27. Okay. Package B is not smaller than package A. Now, the question that is posed is, where is package A? Now, how can we answer this question automatically? Let us quickly see that. Now, here what we will do is, we will just forget about this part for the time being, we will add another literal to each clause that will come from the negation of the theorem. For example, here our negation of the goal, so all packages in room 27 are smaller than those in room 28, can be converted in the clausal form in this way. All right. Right, because all packages in room 27 are smaller than those in room 28. So, x is a p x and p y, and in x 27, that means package x is in 27, package y is in room 28, and x is smaller than y. Now, if I convert them in clausal form, I get this. A is a package, B is a package. A is in room 27 or A is in room 28. That was the problem here. Package A is in either room 27 or in room 28, and package B is in room 27, and package B is not smaller than package A. Now, my question is, in which room is A? That is, I have to prove that there exists some room number, there exists u such that in I standing for in, A u, A is in u. So, that is my goal query. So, I have to negate it for resolution, all right. Only thing, in order to get this, just look at this. I will just go a little slow. So, the negation of the clause is this. It is straightway taken from Nilsson's book. If those of you who have got this can look into this. Not A u, and only thing that I have added is or. For this u, I have got an answer literal. Let us see what happens. As I go on resolving this, obviously, I will select a clause which can resolve this out. So, I take this and I can resolve it with a substitution of 27 for u, all right. Otherwise, this is not substituted. So, u is substituted with 27 and I get the resolvent A 28. My resolvent becomes this. And with this, now I look for a particular clause which can resolve this out. I take the first clause and as I resolve this, I resolve it with a particular substitution, that is y is replaced with A, and based on that, when I go on doing it, I am remembering the resolvent, remembering the substitution, and in this way, as I come here, I substitute this, and ultimately when I get this contradiction, my this leaf node will come to 27 and that is my answer. Just see that in the normal resolution case, this part was not there, this part was not there. I would have started with this and ultimately I would have come to a null clause here. But if I start with this, if I start with adding with the negation of the goal clause, negation of the goal, the clausal form of that, or I put this answer of that literal u in which I want to hold the answer, then the substitution values will automatically put me that result that I want and that will come as the leaf node. Isn't that interesting? So, the same resolution method can be applied to carry this out. So, in this lecture, we have seen that we can apply the resolution refutation method for the case of predicate logic with some additional techniques that we apply, which we have discussed, the clausal form, the unification part, and also we can apply this to find out answers to some questions by applying it in an intelligent manner. Thank you.